Good evening, everyone. My name is William D'Alessandro, and I'd like to welcome you back to another Tech Talk in our series sponsored by Remake Labs. Today, we have the pleasure of welcoming Jeet Patel to give us a brief talk on database management. So without further ado, I'd like to pass it on over to you, Jeet.
Thank you, Will. Before we get started, I just want to thank Remake Labs for sponsoring this tech talk. So today we are going to be talking about database management. So what is database management? Database management refers to the actions a business takes to control and manipulate data to meet certain conditions throughout the entire data lifecycle. Database management has become much more important as the volume of business data has grown. Rapid data growth can create various problems, such as poor application performance and compliance risk, to name a few. Database management can help with preventing the negative effects of data growth. It does not have one goal, instead it has multiple. Some of these goals include improving performance, storage optimization, efficiency, security, and privacy. By controlling data throughout its entire lifecycle, organizations can prevent events that negatively affect efficiency and revenue, and also boost data integration for greater business intelligence. So let's talk about how the large amounts of data can be handled. Now that we have talked about what database management is, how do we actually handle all the large amounts of data? The answer is the Database Management System, or DBMS. With the increase in internet users, a staggering 90% of the world's data has been created in the last 2 years. As the volume of data continues to increase, the need for database management systems to effectively handle business data becomes increasingly critical. So let's talk about what a database management system is. A database management system is software that helps organize, store, and retrieve data from a database. It involves various functions that work together to ensure that the data is accurate, available, and accessible. A database management system consists of three elements. The first element is a physical database that contains the data. The second element is a database engine that helps to access the data and modify its contents. And the last element is a database scheme, which presents the logical structure of the data stored in the database. So now let's talk about some of the many functions of the database management system. There are several functions in a database management system, but we will only talk about a few important ones. The primary function of a database management system is to store data in an organized manner, ensuring efficient retrieval and updating. It systematically manages data in records, tables, and fields, allowing for data to be quickly accessed, modified, and stored. Another function of a database management system is data integrity and security. Data integrity is maintained by ensuring accuracy, consistency, and reliability. A database management system applies constraints and rules to prevent invalid data entries, which preserves data quality. It employs security features like user authentication, access control, and encryption to protect data from unauthorized access. Transaction management is another important function of a database management system. A database management system supports transaction management to ensure that database operations are performed reliably and adhere to ACID properties. ACID stands for atomicity, consistency, isolation, and durability. Atomicity ensures that all steps in a single database transaction are either fully completed or reverted to their original state. No changes are made to the data if any part of the transaction fails. Consistency guarantees that data meets predefined integrity constraints and business rules. Even if multiple users perform similar operations simultaneously, data will remain consistent for all. Isolation ensures that a new transaction accessing a certain record waits until the previous transaction finishes before it commences operation. It ensures that concurrent transactions do not interfere with each other. The last property is durability, which ensures that the database maintains all committed records, even if there's a system failure. It will guarantee that when ACID transactions are made, all changes are permanent and non-impacted by subsequent system failures. Most relational databases are ACID compliant, and it is very important for reliability and consistency. The last function we will talk about is data backup and recovery. A database management system provides data backup and recovery mechanisms to protect against data loss due to hardware failures, software bugs, or other unforeseen events. Regular backups and recovery procedures ensure that data can be restored consistently in case of a failure. Now that we have talked about some functions of a database management system, let's talk about some of the types. Four main types of database management systems are the relational system, the network system, the object-oriented system, and the hierarchical system. A relational database management system stores data in tables structured in rows and columns. Each table represents a different entity, and relationships between entities are established using keys, such as primary keys and foreign keys. The relational database management system uses structured query language, or SQL, for data manipulation and retrieval, making it easy to do complex queries, joins, and transactions. This system is very popular due to its simplicity, flexibility, and ability to handle large volumes of structured data. The next type is the hierarchical database management system. This system manages data in a tree-like structure where each record has one parent and potentially many children, creating a parent-child hierarchy. This allows for efficient data retrieval and is especially beneficial for applications with predictable access patterns and a clear hierarchy, like organizational charts and file systems. The hierarchical database management system is fast for specific queries, but can be limiting when dealing with more complex relationships or when the data model needs to evolve. The network database management system extends the hierarchical model by allowing more complex relationships between records. This model organizes records in a graph structure, enabling each record to have multiple parent and child nodes, forming a network of interconnected nodes. Because of this, it can handle many-to-many relationships and complex data models efficiently. It is particularly useful for applications like telecommunications and transport networks. The last system is the object-oriented database management system. In this model, data is stored as objects, similar to those in programming languages like Java or C++. Each object contains data and methods that operate on the data, allowing for more complex data structures and relationships. This system is particularly beneficial for applications that require the modeling of complex data types, such as multimedia applications and scientific research, where the traditional relational database may not be able to represent real-world entities and their interactions. The last thing we will discuss is a database architecture that has been receiving a lot of attention in recent years, database sharding. Sharding is a database architecture pattern related to horizontal partitioning, the practice of separating one table's rows into multiple different tables, known as partitions. Each partition has the same schema and columns, but also entirely different rows. Sharding involves breaking up one's data into two or more smaller chunks called logical shards. The logical shards are then distributed across separate database nodes, referred to as physical shards, which can hold multiple logical shards. Despite this, the data held within all the shards collectively represent an entire logical data set. So now let's talk about the benefits and drawbacks of database sharding. One of the main benefits of sharding a database is that it can help to facilitate horizontal scaling, also known as scaling out. Horizontal scaling is the practice of adding more machines to an existing stack in order to spread out the load and allow for more traffic and faster processing. Having the freedom to scale horizontally makes your setup much more flexible. Another benefit of database sharding is faster query response times. When you submit a query on a database that has not yet been sharded, it may have to search every row in the table you're querying before it can find the result set you're looking for. By implementing database sharding, queries have to go through fewer rows and the results are returned quicker. There are some drawbacks to sharding as well. The first difficulty is that implementing a sharded database architecture is highly complex. Even if done correctly, it can impact team workflow because users must manage data across multiple shard locations, which could be disruptive to developer teams. Another issue is that once a database has been sharded, it can be very difficult to return to its original structure. Any backups of the database made before it was sharded won't include data written since the partitioning. And with all that being said, we have reached the end of our talk today. We are just about out of time, so if anyone has any questions, feel free to reach out to me by email or LinkedIn, and I will answer your questions there. Here are some of the resources that I used. And once again, I would like to thank Remake Labs for sponsoring this Tech Talk, and I'll pass it back over to you, Will.
Wow. Thank you so much for that informative talk. And thank you everyone for coming out tonight. We'll see you at the next one.